Alrighty, so in this video we're going to talk about the when forces are applied to an object at an angle. So normally, and you can see my question on here, normally we have said a box is on the ground, I'm going to push it to the right, friction is going to act opposite, gravity's down, normal force is up. And that's totally fine and that's right when I am applying a force that is perfectly horizontal. So I'm pushing a box from behind and I'm pushing it, straight forward. However, if you can imagine this box here in my picture on the left, I'll erase that one, is a shopping cart. Let's say there's the handle of the shopping cart. You can imagine somebody pushing the cart might be kind of leaning on it, like if they're tired of walking or whatever, they might be leaning on the cart. And so they're pushing it at an angle like this. They're moving it forward, obviously, because they're walking, pushing it, but they're also leaning on it. They're also pushing it into the ground, right? If you can imagine like a nice grape sitting on a counter. There's my grape sitting on a counter. There's a certain amount of force of gravity acting on that grape, holding it to the counter. There's a certain amount of normal force holding it up on the counter so that the grape doesn't magically sink through. If you were to accidentally, oh, it's on the counter. I'm actually going to put it on the floor. It's on the floor. If you were accidentally going to step on it with your shoe, you have now added an increased force pushing down on it. The force of gravity remains the same from the grape because the grape's mass didn't change. However, this applied force you are adding to it, that's supposed to be straight down, is increasing the amount of force the grape feels. The grape still does not go through the floor. Therefore, the normal force must increase so that our down forces applied in gravity must equal our normal force. Let me show you that one more time here. And this is going to start applying to the picture I have on the left here. So if we had on the floor some object, here's a little cardboard box. A little solid block. There's a little solid block, weighs 1 kilogram. While the force of gravity currently on the block equals mass, M equals mg equals 1 times 9.81. And of course, you can see that the force of gravity the block experiences is 9.81 newtons. Well, since it's not sinking through the floor nor floating away, the force normal, the force the floor must exert on it has to be equal to the force pulling it down, 9.81 newtons. So they must be equal. When you increase or when you add a force down, so I'm now going to step on this block with enough weight to apply 50 newtons down, well, all of a sudden, we now have two forces down. We have Fg and force of gravity, Fg plus my applied force are both acting down. My normal force is still acting up, but since the block isn't, breaking through the floor, this force heading down has to equal the force up. And so when we add those together, we get 59.81 newtons. That must also equal your normal force. Now notice these forces are traveling in the negative direction. And so that equals your negative normal force. So your positive normal force equals a positive 59.81 newtons. They have to equal the exact same force or else the box will sink through the floor. And so when we look at this diagram here, notice, actually, let me draw a dashed line here. We're leaning on our shopping cart handle, pushing down kind of, because we're leaning on a little bit, but we're also pushing it forward. The angle our force is applied is used to say how hard down, that's this one here, how hard down are you pushing? If you're leaning on this handle very heavily, the angle you're pushing might be like this. It might be like a 60-degree angle, where most of your weight is actually pushing in the y direction, pushing down into the floor, and a smaller portion of what you're pushing is actually going forward. And so here you can see this is our vertical component of how hard we're pushing down on the box. So we're actually like adding mass to the box. And then this dashed line is basically saying how hard forward we're pushing the box. And so if we were told here that we were applying a 60 Newton applied force, that's this side of our triangle. We can use sine and cosine to figure out the other two sides. So we do 60 cosine 30 to equal this side, 51.96 newtons. And the other side, 60 sine of 30 equals 30 newtons. And so we can see even though our applied force is 60 newtons, since it's at an angle, this value is not usable to us. We must split it into an x component and a y component. The ones we're going to end up using when we talk about forces and inclines, we won't use x and y component. We'll call it parallel and perpendicular. We'll see that soon. But here I'm just going to call them x and y. And so I'm pushing forward with this much force. And I'm pushing down with this much force. So knowing that this is a 3 kilogram box, we can say, okay, well, what is our force of gravity on the box? Well, of course, force of gravity equals mg. So 3 times 9.81 equals a force of gravity of 29.43 newtons down. Notice I've added an extra 30 newtons down. So that is my force. I can't really fit it in there, but that's my force applied down. I'm going to call it force applied y because it's in the up and down the y direction. And so our combined force is down, Fg plus force applied y must equal our normal force, or else the shopping cart will sink through the grocery store floor or it will float away. And we just need to note that they're opposite directions, so one will be negative and the other will be positive. So I'll just throw a negative there. So 29.43, and this is in the down direction, plus negative 30, whoops, that's weird, 3, equals negative 59.43 newtons equals negative force normal. So force normal, of course, equals positive 59.43. So that's essentially how hard the ground must push back up on this shopping cart to prevent it from going through the floor, because we're pushing it into the floor. The floor must resist that, or else it's going to go through the floor. Then we can say, okay, how much friction will be acting on this block? Well, if we knew this block was not accelerating, that means F net must equal 0. And we have a force of friction in the rear, like going rear, backwards, and we have this portion of how hard we're pushing forward. So we're actually pushing forward with 51.96 newtons, and since we're not accelerating, friction must be in the opposite direction of 51.96 newtons, right? Because if we're not accelerating, force of friction, negative force of friction equals force applied in the x direction. So it's really important to see when your force is applied at an angle. You need to break it up into its x component and into its y component so that you can see, well, technically you're pushing partially into the ground. You're actually increasing its the force the ground must exert back on it. You haven't changed gravity, which will change its normal force. You can look at its x component in order to see how much friction the object will experience. We also could have found friction without even using this value. We could have been given a coefficient of friction, and now that we found our normal force, we can multiply that by our force of friction. I know I wrote one here, disregard that. That one I didn't even use in calculations. I have no idea what it would be relative to this picture. But since the force of friction equals coefficient of friction times the normal force, this normal force that we calculated based on the gravitational force plus the force applied that we were using pushing it into the ground, that is used for our normal force. One of the common mistakes is they'll say, oh, Fg equals Fn, so that 24.93 newtons that we got from Fg equals Fn, and then they'll plug that in here times the coefficient of friction to get the force of friction. But the force of friction will be stronger because there's more normal force from the floor acting on the box. So let me clean this up and just briefly show you one more time quickly without the math how this works in multiple, or when you have a force at an angle. And I'm going to actually show a force going a little bit in the up direction. So imagine you're, imagine you are pulling a sled at this angle. Oh, my pen is doing something weird. One sec. So you're pulling a box at that up angle. While you're doing that, you're partially pulling it forward, and you're also kind of pulling it off the ground. If you can imagine a really light sled, if you're pulling it behind you, kind of, and obviously you're kind of pulling up, you'll notice that the front of the sled kind of bobs up and down, right? Because that sometimes the force up helps it actually pull the front of the sled off the ground, because you're technically pulling. I don't know why my pen is doing that. Okay, I'm going to use my mouse. It will look worse, but I'm going to use my mouse to draw from now because my pen is being weird. So technically, we can draw a dashed line to say, okay, how hard forward am I pulling a box versus how hard up am I pulling a box? And if we said F net doesn't necessarily equal 0, we don't know if this is accelerating or not, and we wanted to calculate the force of friction on the box, and I gave you maybe a coefficient of static friction or kinetic friction equals 0.3, let's say. Well, we know force of friction equals coefficient of friction times the normal force. Well, we need to figure out the normal force. Yes, gravity is acting on this, let's just call it a 1 kilogram object. So we know force of gravity equals 9.81 times our mass of 1, but that does not equal our normal force because we're pulling this off the ground a little bit. The ground has less work to do to hold it up because I'm pulling it off the ground a little bit. And so we can write down in here that there's 9.81 newtons down. If I'm pulling, let's just say with 10 newtons at a 30-degree angle, let's say, we can easily find 10 times cos of 30 equals 8.66, which is this side. So that's how many newtons I'm applying pulling forward. And then of course 10 times sine 30 should equal 5. And so 5 newtons is how hard up I'm pulling. Well, the object itself is pushing into the ground with 9.81 newtons of force. I am pulling up with 5. And so the normal force, in order to keep it from sinking into the floor or flying away into space, we would say the normal force plus our applied force in the y direction, because we're lifting it now, not pushing it into the floor, equals the force of gravity. And so we don't know the normal force, so I'm going to subtract the force applied from both sides. So force normal equals 9.81 minus 5, and of course that equals 4.81. So the normal force equals 4.81 newtons. This is now our normal force, which we plug in here. So 4.81 newtons times 0.3, our coefficient of friction, means that the force of friction this box experiences is 1.443 newtons. So if the question asks for force of friction based on this angle we're applying a force, that's what it would be. The question could also ask us, what's the acceleration of the object? Well, that means we know there is a net force. We can see that the up and down forces have to be equal or else it's sinking into the ground or floating away. But we know how hard forward we're pulling, and we know how hard friction is trying to resist us. And so F net equals 8.66 newtons, that's our forward force, plus, and our friction is against us, so it's a negative 1.443. And we get 7.217 newtons of net force. And so finding the acceleration would be F net equals mass times acceleration. So just divide that by mass, and the mass is 1. So that would be your acceleration is 7.217 meters per second squared. So when you're using an angle on an object, make sure to split it into the x component and the y component, because you're partially pushing or pulling it forward, and you're partially, either in this last case you did, lifting it off the ground a little bit to lighten the normal force, or like this first example, you're pushing it a little bit harder into the floor, increasing how hard the floor must push back on it.